Good day, everyone. Today I will discuss our activity about flange coupling design. This activity focuses on bolt shear, flange injection shearing, and protective flange coupling design. I will first present the given problem and then explain the solution. So the first problem, a flange coupling for a 35 mm shaft uses 6 bolts on a pitch circle diameter of 125 mm. If the shaft transmits 800 Newton per meter of torque, calculate the required nominal diameter of the bolts. If allowable shear stress for the bolt is 56 MPa. So the given our shaft diameter, which is 35, pitch is 125, number of bolts 6, and torque of 800 Newton per meter, then shear stress of 56 MPa. So first we determine the radius of the circle. So 125 times 2, 125 over 2 is equal to 62.5, which is 0.0625 meter. So the torque equation is torque is equal to NFR. By substituting the values, 800 is equal to 6 times F, which is force, times 0.0625. So the force acting on each bolt becomes 2,133.33 Newton. So next, we use the shear stress formula. So shear stress formula is F over A, then we substitute the value. 56 times 10 to the raise of 6, which is 56 MPa, is equal to 2,133 over pi d squared over 4. So the diameter now is 6.96 millimeter. So therefore, the required nominal bolt diameter is approximately 7 mm. So for number 2, for a flange coupling on a 300 mm diameter shaft transmitting a power of 3 megawatts at 100 RPM, the flange thickness is 100 mm and the half diameter is 600 mm. So calculate the induced shear stress at the junction where the hub meets the flange and compare it to a safe limit of 60 MPa. So the solution given our shaft diameter, which is 300 mm, power of 3 megawatts, speed of 100 RPM, flange thickness is 100 mm, half diameter is 600 mm, and the safe shear stress is equal to 60 MPa. So first, we compute the transmitted torque power using the formula of torque is equal to 60 times power over 2 pi n. By substituting the values, 60 times 3 times 10 to the power of 6 over 2 pi 100. So the torque becomes 286,478 Newton meter, or 286.478 kilonewton meter. So next, we determine the shearing area at the flange junction. So the formula for area is equal to pi d squared over 4. So by substituting the values, area is equal to pi times 6 over 0.1, so we can get the value of 0.188 meters squared. So solving for the shear stress is equal to 286,478 times 0.5 times 0.6 over 0.188. So the induced shear stress is 5.07 MPa, which is much lower than the safe limit of 60 MPa. So the flange junction is considered as safe. So for the last problem, design a cast iron protective type flange coupling to transmit a 15 kilowatts at 900 RPM with a service factor of 1.35. Then calculate the required shaft diameter and the thickness of the protective circumferential flange based on standard proportions. So these are the following givens: power of 15 kilowatts, speed of 900 RPM, the service factor of 1.35. So first, we just calculate the design torque. So torque, as we all know, the formula is P times 60 over 2 pi n. So by substituting the values, we can get the torque of 214.85 Newton meter. And next, we determine the shaft diameter using the torsion equation. So by having this formula and to solve it, we can get the shaft diameter into 30 mm. Then last, we calculate the thickness of the protective flange using the standard proportion. So we have a 0.25 diameter times the diameter of the shaft, which is 30. So we just multiply it, then we can get the value of 7.5 mm. So the required shaft diameter is 30 mm and the protective flange thickness is 7.5 mm. So that's all.